Welcome to Newton's Classroom, the physics class every robot should attend. This is a fun title because it's a fun live stream. We have some very special guests here. I'll introduce them in just 1 minute. But thank you for joining us for the OpenUSD Insiders live stream. I'm Edmar, I'm the community manager for NVIDIA Omniverse, and today we're going to be exploring the Newton Physics Engine, a new open source GPU accelerated platform created through collaboration between NVIDIA, Google DeepMind, and Disney Research, and managed by the Linux Foundation. It's built on NVIDIA Warp, and as you can see, we have Mohammed here, so super exciting, one of our most favorite topics in the community, and it's also built on OpenUSD. Newton delivers high-fidelity real-time sim that closes the gap between virtual and physical robotics. That's the best way to say it. We're going to unpack its modular architecture, solver design, and ecosystem adoption, covering rigid and soft-body dynamics, cloth and granular materials, and how differentiable physics unlocks gradient-based learning for frameworks like Isaac Lab and MuJoCo. Let us start. I'm going to cover the news, including GTC and stuff, which I'll cover that at the end of the live stream. So don't hang up when we finish talking about Newton. There's still a little bit more, but we want to dive right into things because we have a lot to unpack and some very special guests here. So starting from next to me here, Asari, thank you so much for joining us.
Yes, thanks so much, Edmar. And hi, Mo. Hi, everyone. Thanks for joining our live stream today. I'm Asaveri. You might have seen me on last week's live stream as well. I'm a tech marketing engineer. I work on some of our robotics platforms like Isaac Sim and Isaac Lab. And just super excited to learn from Mo today about Newton and to hear all about this.
Amazing. I'm so glad to have you here. You're now a veteran, official co-host of these live streams. Mohammed, it's so great to have you here. Whenever you're here, there's so much excitement in the chat because people are so excited about Warp especially, and now Newton. Tell everybody who didn't catch you on your previous appearance a little bit about your background and what you're going to be covering today.
Sure. Excited to be here. So Mohammed Mahajirani, my name. I'm a product manager at NVIDIA. I work on NVIDIA Warp as well as Newton as a product manager. So I'm here to tell you all about Newton today. Last time we talked about Warp.
Amazing. Okay. So we're going to dig right into things. Now, reminder to everyone watching, we are going to be taking your questions in the chat. So feel free to post let us know where you're watching from. That's always great to see. Let us know any questions you might have, materials along the way. Our great producer, Amelia, and Asari will both be watching the live chat very closely. And we're going to be making sure to asterisk some really important ones that we think will help a lot of people. And we'll circle back to those at different points during the show. So if we don't get to your question right away, don't worry about it. We're making note of them, and we're going to try to hit all of them we can. And then afterwards, you can always go to our Discord server. Say, for example, you're not watching this live. You can go to the Discord server and follow up on this live stream anytime in a specific dedicated thread we have on that. Okay, I'll pass it off to you guys now. How do you want to get started?
So maybe I can start sharing the screen.
Perfect.
I have a presentation prepared going over some of the context of Newton, why we built Newton, and then some of the key features and some of the contribution from the community already, which is pretty impressive. So yeah, let me start sharing my screen.
Amazing. Look, we already got some excited people grabbing their popcorn.
And this is so cool too, because we got one of our first questions. What specific challenges in current robot simulation does the GPU accelerated Newton physics engine aim to resolve? And this is great, right? This is exactly what today's live stream is about. So I'm glad that we'll be getting into this now.
Amazing.
Exactly. Yeah, definitely. That's a piece that I'll probably cover at the beginning. Perfect. Lovely.
Okay, we see your screen.
Yeah, do you see screen? Okay.
Yes.
I see it too. So let me start to give you some context on why Newton. So one way to look at robotic is through its different spectrum of different applications that it has. Of course, we are very familiar with the functional robots that has been running for decades in the industrial settings and manufacturing. Programmable robots that repeat tasks over and over. They don't interact with humans as much. And so that's on one end of the spectrum. And the other, we have the type of robot that maybe categorized as entertainment robots, the type of things that probably you've seen in Disneyland. These type of robots are there to help with the storytelling, bring joy to people, interact with people to some level. but not too much. And their main purpose is entertainment. And then maybe in the middle of the spectrum, we have robots that are more collaborative in a sense, and they're companion robots. They're maybe human and robot would be categorized here. These are the type of robots that would probably interact with human much more, at the same time collaborate with them to function in the environment. And so as soon as you bring those two in together, human and a robot, you're dealing with a lot of different levels of complexities. So wherever you sit in this spectrum of applications, you are dealing with complexity at different levels of your stack. So whether the way you perceive the environment through your sensory inputs, whether your tactile sensors or RGB depth camera or LiDAR, torque sensors, joint encoders and things like that, whether you're working on the cognition or intelligent piece where you basically make sense of those sensory inputs and basically decide what to do next to interact with your environment, as well as how you interact with your environment through your articulation and actuators and the control system, lower level control system. Wherever you are in this kind of vertical stack, you still deal with complexity. And of course, as when we talk about the application in the middle with collaboration, functional safety, security, all those become much more important. Luckily, physical AI and AI in general is there to help us solve these complexities across the board. And today, we know that data is key in solving those challenges through AI. And the way we look at, we've been doing research and engineering in this area for a while now. And the way we look at data as it serves robotics and physical AI is through a pyramid, where at the top of this pyramid, we have a lot of real, demonstration from real data from real robots. So these have a lot of information embedded, encoded in them, because they're coming from real sensors, real actuators, real robot operations. Though obtaining these data is expensive, could be dangerous. It's could be costly, and not everybody can do it. So the scaling factor there is limited. At the bottom of this pyramid, you have internet scale data. The type of data we've trained our LLMs on. We could use similar type of data for training these models that would serve particularly the cognition aspect of the simulation, training the VLAs and other type of model that run the kind of intelligence piece of the robot. RGB videos, at the internet, you have plenty of it. You could use plenty of that, though that is not in a robotic format, and so there are limitations there. But in the middle of this spectrum, we have synthetic data. So synthetic data is what you have much more control over. You would be able to generate that from simulation, from first principle simulation. And then you can scale it through different methods. You can randomize it, you can scale it, whether it's on the graphics side or whether on the physics side, physics of motion. So synthetic data is kind of the sweet spot. But at the end of the day, you need all these different levels of data to be able to address the complexities of the robotic stack across a spectrum of applications. So simulation, which is the core of synthetic data generation, relies on governing equations. So on maybe when we think about synthetic data, we have some part of like RGB data, where we through rendering and graphics simulation we kind of obtain. So that piece has been kind of much more advanced. We have really high fidelity rendering capabilities. On the physics side, the physics of motion, the fundamental equations hasn't changed for more than a century actually. However, there has been many different flavors of how to solve those equations numerically, and so there hasn't been although there has been different flavors, there haven't been a kind of a unified way of kind of addressing the physics problem. So if we solve that, if we have the right framework to do physics simulation, physics of motion and control and all that, the dynamics, multi-body dynamics problem, basically, then we can eventually scale this data through synthetic data generation and then serve the physical AI problem that we're solving. So we went to the drawing board and said, what would be, if there is no method or there's no framework that's out there that could solve this problem, what would it take to build one? And what are the key requirements of such a physics engine? So this is basically at the requirement brainstorming. So one of the things that came to mind is, like, because of the fact that there are different flavors of solving, formulating those fundamental equations and solving them numerically, this framework needs to be, this physics engine needs to be modular enough and extensible. So the active research that's being done could be kind of pulled in, and the framework that we're building could be extended. So we've made a lot of advancement in rigid body dynamics simulation. However, we haven't made as much advancement in soft body simulation. So soft body simulation usually is something that FEM models and high fidelity simulation has solved, and those are not scalable for robotics. So we think modularity and extensibility will allow this physics engine to be extended. Of course, it needs to be open so that the community can start building upon it. The graphics side has been accelerated. It's actually how GPU started, actually. So however, the physics of motion and multi-body dynamics hasn't been accelerated. There are not many examples out there that before, that were like GPU accelerated physics, and for specific reasons that are understandable. If in the requirement realm, one of the things we want to consider is that we don't want to start from scratch. So there are solutions out there that have been proven for robot learning in the past couple of years, including MuJoCo. So MuJoCo has been widely used and published in robotics research and industry. So we want to leverage that. So we don't want to throw that away. Another requirements we thought of is common data interchange. So there needs to be some common way of bringing your assets and build your worlds and environment in the simulation. So if you unify that would be much easier and more streamlined. Of course, we're not going to limit you to that common way, and we probably would allow you other ways to support bringing your assets into the simulation. But we wanted to have kind of unify that. We have OpenUSD there that could help. Differentiability. So in a world of AI where we have we train neural models, we do advanced optimization problems using deep learning frameworks like PyTorch or JAX. If you have your simulation be capable of computing gradients, how the output changes with respect to inputs or parameters of your system, you could actually couple your simulation with your training or optimization frameworks, and then you could achieve really interesting things like you can solve optimization problem across you can do design optimization, you can do control optimization, or model training with the simulation in the loop, which would save you a lot of simulation runs as well. And all of this, if you have a modular system that's extensible and you have multiple different solvers like MuJoCo, and then let's say XPBD and another solver, as a user, you don't want to deal with different APIs. So you want to kind of give you a easy to use and simple API, a Newton API that you could use to interact with these different solvers in underlying solutions, and also couple them together. So if you put all of this in one frame, you see that this is a very kind of a high bar to meet, and there's no one company that could do this alone. So that's why we came together with our friends at Google DeepMind as well as Disney Research We've been working the past year or two together to basically build this up and address these needs. And at GTC San Jose, March 2025, Jensen announced Newton, which is there to address all those requirements together. So at Coral a couple of weeks ago, we announced that Newton would be a Linux Foundation project. So it's going to be managed by Linux Foundation. It's going to be contributed by these three organizations, kind of as founding members, and it's open source under Apache 2.0. And we just getting started. So that's a little bit of a context. What's going to come next? I'm going to talk a little bit about architecture, some of the key solvers that are there already. And at the end, I'll talk a little bit about the ecosystem adoption. I just want to pause a little bit and see, Asa, Mar, is there anything you think that we need to address from the questions that relates to?
Yeah. We do have a couple of questions. I think maybe we can do one or two right now.
Yep.
So there's one that says, how does the unified API specifically expose the gradient information from the differentiable physics engine to external frameworks like MuJoCo?
Specifically expose the gradient information. So like, actually, I should start with a caveat that, so I'm going to talk a little bit about differentiability down the road when I talk about architecture. At the beginning, the phase we are at the beta of Newton. It's not general availability. Not all of the solvers are differentiable, but once that basically differentiability comes with a cost. So we want to achieve performance. You want differentiability in certain scenarios where you want to solve an optimization problem, or a control optimization, design optimization, or a training. So you don't want differentiability all the time, especially when you want performance. So there's a cost for that, and that's why we're very carefully evaluating, how to design that and make that available. But the gradients information. So the differentiability of Newton comes from Warp, NVIDIA Warp, which automatically automatically differentiate the simulation output with respect to, gives you the gradients of the output with respect to inputs through automatic differentiation, which is a method. So basically, there are API calls that kind of help you get the gradient. First of all, opt-in to be differentiable. So that's an opt-in feature in Warp. Second of all, to access that gradient information. And then we have interoperability in Warp, which is the underlying framework under Newton. We have interoperability with PyTorch and JAX at the gradient level as well as at the data level. So you have a zero copy data between these two frameworks. So once you have a gradient or like a data in the Warp array, you can pass it along to PyTorch, for example, without copy. You have gradient, basically gradient interoperability at the gradient level between PyTorch and Warp. As a result, Newton will benefit from it. For JAX, it's coming in the next release of Warp, but it's not there yet. So that's how I would say there are already APIs in Warp that Newton could benefit to pass along the information to those DL frameworks. Okay.
That's awesome. Thanks, Mo. And then I see one more question we can take before moving ahead. And this is more related to the Spark. So it says, now that Spark is starting to be available, can you confirm whether or not it will be able to run Isaac Sim and Lab? So I think I can confirm, yes, it does run on the Spark, Sim and Lab, because we have run it before. It's great to hear that yours is arriving around November 10th. You can definitely start running some of the tutorials we have on the website on your Spark. Mo, if you want to add anything to that, feel free. And if not, we can move ahead.
Yeah, so that's also similar for Warp and Newton, which are the underlying, Warp is kind of below Newton, Newton is below Isaac Lab, let's say. That's how you can look at it in terms of the stack. And Warp, idea behind Warp is that we wanted to run wherever CUDA runs. So as these new hardware architecture come into play, one of the things that we do, one of the very first thing we do, we are ensuring that Warp, as a result, Newton would run on those. And DGX Spark at Coral, we had actually demonstrated that Isaac Lab experimental branch with Newton backend runs in Spark, which was pretty interesting. If you were there, actually, it's see. So yeah, I can continue maybe, go a little bit deeper into the, is that okay, Asa?
Yes, let's go ahead.
Okay. So we talked about requirements. Now let's see what Newton looks like at a very high level architecturally. So we talked about modularity and extensibility. So some of the key modules that are there in Newton are solver module. That's where let's say we have, we basically solve for the constraints, equality constraints, contact constraints, and then you integrate over time and advance the simulation forward. So the solver is a very key piece of the Newton, and that's where a lot of the innovation comes into play. We have a collision library where we're very excited about this. It's going to kind of come out in the next kind of beta release. That's where we're hoping that we could kind of, this is the common denominator between a lot of different solvers that are like simulation engines that are out there. So there's a collision detection and the contact generation, and then there is the solving piece. So we think that if you have a really robust and efficient contact purpose-built for Newton on Warp, that then that probably we could easily kind of swap different solvers and kind of connect different solvers with different collision detection models. And that's where we could have also, we think that could be extended. That's where, two objects are evaluated, whether they're intersecting or not. Basically, we kind of find the contact points and then apply the forces. We have state, all the time varying elements of our simulation. So position, speed, velocity, and acceleration, and model all the non-time variant aspect of our simulation. And so this runs under Apache 2.0, and this is OpenUSD compatible, with meaning that it can accept assets from that are in USD format, but it's not limited to USD. So we accept MJCF as well as URDF. As a very first, so I told you that Newton itself is not necessarily an NVIDIA product. It's a Linux Foundation project. And however, we at NVIDIA, one of the main use cases we have for Newton is integrating it in our Isaac stack, starting with Isaac Lab, where we do a lot of RL. And that's where we want speed and performance and GPU acceleration. So as a very first step, we've been working very closely the Newton and physics team, as well as the Isaac Lab team, to basically integrate this. Isaac Lab is established product. It's we are 2.x release of Isaac with a PhysX backend. We are starting to integrate this in a separate branch. I think if you go and look at it, and it's already available, it's an experimental branch called, I think, Isaac Lab /Newton or something. And that's where we're doing the kind of the development out in the open. And so we are hoping that to extend this, not hoping, we are actually planning to extend this to Isaac Sim. So Isaac Sim and all the software in the loop, synthetic data generation workflows, we're planning to actually integrate Newton as a separate backend for Isaac Sim as well. But for now, our focus is Isaac Lab. Newton in its entirety is not exposed in the Google DeepMind stack training. They have Playground and MJX. However, the MuJoCo solver, which is called MuJoCo Warp, the accelerated version of MuJoCo C, is exposed in their stack, and that's how they're benefiting from the acceleration that Warp provides. And all of this is kind of accelerated through CUDA and Warp. And so I think it's important. So this is actually a full picture of like a high level of architecture. And I'm going to dig a bit deeper on some of the solvers. But before, I'd like to talk a little bit about Warp. And we had a separate session about this, which we went into in depth, talked about it. And Asa or Edmar, I appreciate if you could link the the last discussion that we had here for the audience might be useful. But a very quick summary, like a 1 or 2 slider summary of what NVIDIA Warp is. NVIDIA Warp is a domain-specific language that's is purely in Python, and it gives you, basically, it enables you to write GPU kernels with the Python syntax, and basically it opens the door for you to start GPU programming with much in a much easier way. So it gives you some really key capabilities. One is it comes with near native CUDA performance through its just-in-time compilation, and it also exposes some of our other CUDA-X libraries that are actually fine-tuned for NVIDIA GPUs, like cuFFT and then cuSolver. So you don't go and write your own FFT every time. So there are ways that you could leverage those lower-level libraries through Warp, and it gives you ease of use. It actually is pure Python syntax. At the same time, we talked about performance. It's not kind of bottlenecked by a Python interpreter. So it has a very unique compilation pipeline where we generate CUDA code under the hood, and then we compile it on CPU for CPU or GPU. And then basically we run it, we cache it, and then we repeat this. So every subsequent run of the same kernel would be much faster. So the pure Pythonic syntax actually make a big difference. It has different methods of kind of programming paradigm, like tile-based programming or SymT programming. And it's purpose-built for simulation. So not necessarily robotic simulation. It's actually very broad. Warp has applications in FEM and CFD and discrete element methods and all those other domains of simulation. And the native data structure and algorithm that is provided in Warp could be used actually to accelerate and make it much easier to write GPU accelerated code for simulation. And we talked about automatic differentiation. That's a key capability. And we also talked a little bit about deep learning framework and Trav, like PyTorch and JAX. It ships with a really solid example, basically gallery, and you can check it out. Gets you started on different domains where Warp has been used. And it is also open source under Apache 2.0. It's simply, you can pip install it. You can start looking at the repository here through this QR code. And one thing I'd like to tell you about, like the history of Newton. Newton actually started as a module in Warp Sim. So Warp has different modules. One of them is like Warp Core, where we kind of address the kernel programming and automatic differentiation and things like that. But then we have an FEM module for PDE, partial differential equation solve. That's used in kind of CFD and other domains and elastic simulation, things like that. And then we had one dedicated for multibody dynamics, which was Warp Sim, and that was the origin of Newton. So we at 1.10 release of Warp, which is coming in a few weeks, actually beginning of November, we're actually removing Warp Sim. We've been deprecating it for, I think, 2 release cycles now. We are actually moving everything to Newton. So a lot of the examples I showed in this previous slide that were robotic simulation specific are migrated already to Newton. So a little bit of history about how Newton actually came to be. And we've started seeing a lot of people who were Warp Sim users transitioning to Newton. It's very exciting. And if you were a user of Warp Sim, and now you have questions about how to do the migration, we have a really nice migration guide. I'm going to actually look it up in the Newton documentation that you should look at. I'm going to share here actually, and then maybe you guys can share it with the community.
Awesome. Yeah, you can put that in our little private chat thing here, and we'll paste it in the live chat. So many great comments and questions coming in. Amazing amount of information and nice little announcements here.
Yes.
Thank you everybody for tuning in.
Do we maybe want to take a couple of questions now and then move
Yeah.
on?
Yeah. So I give a quick about this slide. So we've been talking about Warp for a while now. It's been there for 3 years or so, and at different GTC events. Oz Macklin, Lukash, and others have been talking about it. So here's a list of some of these interesting talks. Some of them go in depth into how to use Warp for high fidelity simulation, how it's used in the differentiability of Warp. So really encourage you to look at them. They're an hour long, so it gives you a good quick start on what Warp is and how it's been used for robotics and other applications like CAE. Yeah, now Asa, maybe you can take one.
Yes. Okay. So here is a question. How is the state and collision data unified by OpenUSD and Warp to allow seamless real-time switching between different physics solvers like MuJoCo during a single simulation run?
So, okay, so I have some insights, but might not have all the answers. But what I know is like you bring your assets and content through OpenUSD, and whether depending on the type of system you're solving for, whether it's a deformable or non-deformable, and then under the hood we take care of building a model from that kind of input data in Newton. So we build a Newton model. We talked about different modules, and so you could have a model for a granular material and a model for, or like a cloth, let's say, and a rigid body. So 2 different models, and then you can decide with which solver. The API will allow you with which solver you would want to solve which model. And so OpenUSD kind of job is finishes when the model is created, from what I understand. That being said, OpenUSD today doesn't support, from what I understand, like all the different type of there's no schema per se for all the Newton solvers and all the different types of models you can bring into Newton. However, we're working actively to build a kind of a Newton schema for USD. That's coming down the road. But I think from as far as this question goes, you would bring your asset. It could be actually you can bring one model with MJCF, another with OpenUSD, build the model. We also have a model builder kind of primitive that we could use basically, or like helper that you could programmatically build articulation, without any OpenUSD or any MJCF or URDF. However, you're doing this, your model is built, then you go to solver, and then you could input that model in solver. I think in subsequent sessions and live streams, I'll try to bring an engineering rep to kind of show us some code and kind of dive deeper actually into this. But I hope that this answered the question.
Yeah, awesome. And then we have some, I think these are quicker questions. So is the Newton engine, can it run as an extension of Omniverse AppKit? I think my understanding is it's more like with the release we have upcoming in the next few weeks, Newton will be the kind of default engine. Is that right, Mo?
So for lab, yes. For sim, it would be a bit different. So for sim, we have broader use cases of physics and certain applications. Physics actually is very good for certain applications where you have a really cluttered environment, really large environment. That's where an iterative solver probably is better than something like MuJoCo. That's not robotics. So physics is very good for some applications, and we have users of sim who use the physics backend for those purposes. So we cannot not support physics. So we are thinking of bringing Newton as a separate physics backend. Which one would be default? I think I don't know. It hasn't. I don't think it's been decided yet, but it's in progress. The work has been in progress. We also value that some of our Isaac lab users also build up their stack on Newton. For the sake of simplicity and scalability of Isaac Lab, we kind of, this Isaac Lab experimental branch, we went back and said, okay, how do we do this with Newton? Now we are thinking of bringing physics to the equation as well, but that will probably take some time. So there would be probably 2 branches of Isaac Lab for a while until we consolidate them into the next version of Isaac Lab. But I think it would be, something like OmniNewton kit app. The same way we have like Warp. Warp, we also have it standalone. It's like a pip installable package that you can do like regardless of whether or not you're in Omniverse. We also have a kit extension for Warp to use, to use it in the context of the GUI, or like to work with the Omniverse kit APIs or kit SDK, or leverage like RTX rendering and things like that.
Yeah, that makes sense totally. And then the next question is, will some of the tools be open sourced for developers to code with? Yes, I believe the platform is open sourced. Right? People can actually try playing around with it and exploring with it.
Yes, it's fully open source, and you can, both Warp and Newton are open source. MuJoCo is open source, actually, so it's a good synergy there. Yeah, extensibility without open sourcing is not possible as much. There's a limit to it.
Exactly, yeah. Okay, and then this is, maybe we can take one more for now. We currently have 4 DGX Spark waiting for Isaac Sim. What date will the Isaac Sim and Newton be available for use on them? Already available. I believe you can already test, I guess, with the Isaac Lab 2.3 version, which was released around the last week of September. I think that's something you can already run on the Spark to use Newton with. Is that right?
So, so I think these are 2 different things. So, Newton with Isaac Lab experimental, we ran it on Spark. So that's a separate branch. Isaac 2.3, I think, or 2.2, that's a different branch, and I'm not sure about the state of that. Okay. Whether that supports DGX, but I know that this is, as you said, this is in the works. We want to support DGX in Isaac Lab. Isaac Sim and Newton, as I said, is going to come later on. Integration of those 2. Okay.
Awesome. And okay, maybe we can do one more before moving on. This is more about like a robot controller question. So Warp offers automatic differentiation and DL framework interoperability. Could this enable end-to-end training of physics-based robot controllers directly within simulation?
Yeah, that's the premise. I'm not really familiar with those, different tastes and flavors of those training workflows, but I can tell you that what automatic differentiability enables you is that in this simulation run, once you step the simulation forward, you can kind of collect the gradients, and if you have opted in, and then you could use that, pass that information to your training loop. So basically, you can do in-place training. So this can actually, as this kind of core capability, can unlock different types of training workflows. But I imagine that the in situ training or optimization, I've seen that type of optimization in a CAE domain where we could use, with Warp, you could use the differentiability to kind of loop in a training optimization loop at the same time. So you don't need to run the simulations, collect like different configurations, and then collect that data, then offline pass it on. You could do online, more or less. But I'm not familiar, an expert in that domain. I know the core capabilities. I think that's what it enables. Okay.
Thanks, Mo. Yep. I think we can go ahead.
Okay, so very briefly on some of the design principles that we actually came across designing physics for many, many years, as well, designing and building physics, as well as Warp Sim module that I told you about, that we tried to kind of bring into Newton and kind of, it's guidelines or lessons learned. One is separating physical model from numerical method. So that's when we talked about like model module and solver module, that's basically it. So it's in the service of modularity. So if you have a certain model of articulation with certain collision detection and like chain of articulation, you want to solve that with a XPBD method or with a MuJoCo solver or another solver, you should be able to do it seamlessly without changing the model, now that you're using another solver or another numerical method. So that's one of the key design principles. Another is flat data is preferred over object-oriented programming, and this is in the service of interoperability with DL frameworks, because everything is flat data there, and Python as well. So that's another design principle we kind of carried over from Warp Sim. We talked about differentiability a lot. The way differentiability works is actually go backwards in the computational graph and basically find the gradients of certain output with respect to another input or parameter of your system. And in that, you have to really have more control over your memory. And so you have to be very careful about hidden states. So that's another thing that we've basically enabled backpropagation. That's another design principle we took into account, as well as modularity at different levels. So we talked about like higher level modules, but Newton is actually different pieces of Newton, different whether it's a function or a kernel or a solver, you can actually access those at different levels and only use those. So we are, in that sense, Newton is quite flexible, and this doesn't prescribe a certain way or certain pipeline for building your simulation. And this is actually a reference simulation pipeline. And in the service of previous, like this last point about like take what you need at each level, this is a reference simulation pipeline, but you're not limited to this. So traditionally you would one standard or a canonical way of building a simulation is that you ingest your data assets, build a model, initialize your state, do some control logic. Let's say you're in a Python environment, you do collision detection, broad phase, narrow phase, find the contacts, and then you do solve your constraints, contacts, and advanced simulation. This is one way, and probably a very common way of doing it. But let's say you have your own solvers outside Newton, but you only want to use the collision detection module. You can actually. So you can just import the collision module and deal with that, and then forget about everything else in Newton. So that flexibility, and you can do it at every level. You are interested in a function within the collision detection or a kernel that's used in that uses those functions, you could do that as well. So that's in the service of flexibility. I'd like to talk a little bit about some of the key solvers. So I talked about Warp Sim. Warp Sim actually had some solvers already. So semi-implicit Euler solver, Featherstone solver, and XPBD solver came to Newton from Warp Sim. MuJoCo solver is what we've basically, in collaboration with Google DeepMind, we added to Newton. And this is not MuJoCo C, of course. This is the GPU accelerated version of MuJoCo, which is a re-implementation of MuJoCo for GPU by Google DeepMind and NVIDIA. There is Camino solver. This is one of the contribution of Disney Research. They are working on a really interesting solver for a maximal coordinates system solver that enables you to solve general mechanisms like closed loops. Like a lot of MuJoCo is very good at handling articulations, chain of articulations, but when it's like there are multiple closed loop, like a heavy equipment, it's much more difficult to model and solve with MuJoCo. So Camino is there to solve that problem. The work has been started. It's not there yet, but it will be there soon. We have some very interesting work, some research work, neural solver. So using neural network to actually replace as a surrogate to the first principle solvers that has some integration with Newton that we presented at Coral. And we also have deformable solvers. So vertex block descent solver for thin deformables, like cloth especially. implicit NPM solver for granular material, and different types of sand and soil and things like that. And then Style 3D Solver is actually one of the very first ecosystem contribution at a solver level in Newton. So Style 3D is a company that's specialized in garment manufacturing, and these days fine manipulation of cloth is a very complex hard robotics problem. So that's why they were very interested to bring their solution to Newton, and they have contributed. It's available in the code base in Newton. We're excited about that as well. I'd like to talk a little bit about MuJoCo Warp. So I think if you have used MuJoCo, you know that MuJoCo had published MJX, which is a GPU accelerated version of MuJoCo based on JAX. When our teams start working together and they were introduced to Warp, they start experimenting with Warp, and they found out that actually, if they re-implement MuJoCo in Warp, with Warp, they could get like really impressive accelerations in terms of basically, especially for like cloning in multiple environments, for like high throughput scenarios, and compared to MJX. And there are good technical reasons behind it. MJX, based on JAX. JAX is a tensor programming style where you do not necessarily define kernels. You don't have like fine-grained control, and the compiler decides, build the kernels and then compile them from high-level syntax that you provide. On the other side, Warp is kernel programming and is much more suited for finer control, for conditionals, for loops, for if statements. It's closer to pure like a function. So in simulation, logic, there's a lot of logic in simulation, especially contact generation, collision detection, contact generation, the solver aspects. So because of those reasons, they found out that Warp is more suitable, and they can get like a lot of speed up. So here you see some of the comparisons that we've done on RTX 4090 and RTX Pro 6000, and you see MJ Warp compared to MJX, massive speed up. This will allow you to actually, with the same on the same compute and with the same memory, you could actually scale many more environments for, let's say, RL training. So that's why it's very powerful, this speed up. This is an aptronic locomotion. You see the physics step per second in this benchmark. This has been done recently, this benchmark. And then here's a dexterous manipulation task for a leap hand manipulating a cube. And then here you see more orders of magnitude, hundreds and 200s of speed up, comparing default of MJ Warp with MJX, which is pretty impressive. MuJoCo, let me go back. So MuJoCo Warp, MuJoCo is available as a solver in Newton. Now you can access MuJoCo C through its Python binding. It runs in CPU, and then you can also have access to MuJoCo Warp. So that's two ways you can actually work with MuJoCo. One thing that I talked about, I'd like to kind of a parenthesis. The Warp allows you. It's for GPU acceleration, right? But it allows you also to run the same kernel on CPU. So Warp, and as a result, Newton is not limited to GPU. So if you were to especially do debugging, debugging on GPU is not as easy as CPU. So if the same kernel, the same program that you wrote, you want to run on GPU for RL training, you can at the testing stage, you can run the same thing on CPU, and that will help you debug the code. And so this actually today we use that capability a lot in our CI. So I encourage you to look at that. So Warp and Newton are not limited. Of course, it's not optimized for CPU. So MuJoCo C, if you want really good performance for one environment, for teleoperation, probably MuJoCo C would be C and CPU would be the best kind of avenue. But if you were to like do parallelization and you're after throughput, that's where you would use MuJoCo Warp. Quickly on one of the solvers, like thin deformable solvers. This is specialized for thin deformable. The algorithm is extensible for rigid body dynamics as well as like general deformables as well. But VBD solver today supports mostly thin deformables. It's from a research work that was presented at SIGGRAPH 2024 and 2025. I put the link to the research work that is behind. You can look at it and kind of get more insights on what's behind VBD solver. Here in this example, you see a Franca arm solved with rigid body dynamics, manipulating a cloth that is penetration free, which is at a kind of a real-time performance. It's pretty impressive. So all the contacts are there. There's no penetration when it folds, and there is interaction between. This is a mixed system example between the rigid body dynamics that's solved with either Featherstone or MJ Warp on one end, and then the VBD on the cloth. And so we handle coupling at the intersection of when these two systems come into contact. Another example is implicit MPM solver, material point method, for continuum mechanics, basically. This is also based on, this solver is based on a research that was presented at SIGGRAPH in 2016. At the time, it was not GPU accelerated, and now it's GPU accelerated as part of Newton. Is one of the key solvers that you'll see some of the examples of this being used in by some of the ecosystem adopters of Newton. And when you want to, let's say you have on, these were two examples of like things that are not necessarily rigid body. They have deformable simulation on the other end, and you have basically rigid body dynamic on one end. You need to couple them. So the Newton model supports mixed systems, so rigid, cloth, soil. We're working on cable dynamics as well actively, and we're going to have some exciting news about that as well. So the solvers can run independently, and then you have the API to couple them together. All the demonstrations you saw are one-way coupling. So in the case of cloth being manipulated by the Franca arm, of course, cloth is not applying, in this case, is not applying forces on the Franca arm, and it's probably negligible, that interaction. So one-way coupling would be a really good modeling and simulation practice. But in some scenarios like this Disney droid running on sand, probably as the properties of the sand changes, you might want to see the slip, and some interaction, some impact on the droid as well. So that's where two-way coupling is important. What we show here is shown here also in the animal example I showed is a one-way coupling, but we are working on two-way coupling. And I think this is a very complex problem. Code simulation between different solvers is a complex problem, and that's why open source is really important, right? So we want community, the researchers, experts in physics domain come together and help solve this problem. And one of the things that we hope that we can attain in a longer term is find ways to efficiently couple some of this prominent systems together automatically, like that is implicit. So and that's, if you were, like, that's something probably is already available in some of physics SDK. So yeah, so this is a little bit about coupling. Newton comes with an inverse IK solver as well. Also, I wanted to demonstrate the very quick debug UI that we have for Newton and visualizer. So this is for you to basically enables you to really quickly visualize and interact. We're working on some different types of rendering backends for this, but this is going to stay really lightweight. So if you want like high fidelity visualization, RTX type rendering, you probably need to store the simulation in USD and then open it up in Omniverse to do rendering. But this is great for debugging. You can kind of mouse to spring it and peek at different portions, and you can move parts around, which is pretty handy. This is very similar to Simulate app of MuJoCo. We are at the, when we talk about like releases, we are at the beta stage where we think we have a reasonable API for people to start working with. MuJoCo Warp is the primary solver that we've kind of optimized and like ran some training in Isaac Lab with, and so it's mostly optimized for those. At Coral, Humanoids this year, we released the beta, and we have a lot of interesting blogs that I encourage you to look at. On the left-hand side, this is a very interesting starting point for you to start like looking at how you can use Newton standalone, how for a multi-physics simulation. Like I think what we have there is the cloth, and also how you could train using experimental version of lab with Newton backend for a quadruped walking on a flat terrain. So that's what we have on the left. On the right is the research work about neural dynamics, neural robot dynamics that we presented at Coral. It has a Newton integration in a separate branch. I encourage you to look at that as well. It's a very interesting and state-of-the-art in terms of physics simulation. That's where we take the analytical method out of the loop and we use a kind of a network in place of the solver, but the rest of the simulation framework stays the same. So this is also very interesting to look at. We've shown great validations for with the ground truth simulation data for this what we call NERD, and we've done some sim-to-real transfer as well, and we've seen great success. So this is not there to replace the entire physics engine. Physics engine is a framework that allows you to do collision detection and initialization and things like that. Control logic. This is there just to, for now, is there to kind of replace the solver piece, or like be a complementary solver that you can access in Newton. Before I go to ecosystem, a few quick slides on ecosystem adoption. Is there any questions you guys want to address?
Yes, I think we can do a couple of questions, some quick ones. So I'm already training using physics. So far, so good. If I switch to Warp, will there be any immediate speed advantage?
Yes. Yeah. So in the what we've seen in so I told you that we've started integrating with Isaac Lab, and as a success criteria, we really wanted to see if Newton can, with a MuJoCo backend, MuJoCo solver, can actually how it compares with physics. And we actually put effort in optimizing our MuJoCo Warp as well as Newton, different aspects of Newton to kind of bring it closer to physics. We saw that for locomotion tasks, we are on par with some tolerance with physics in terms of performance, and with manipulation, we are about I think 65% faster for manipulation tasks. Of course, we haven't yet done very comprehensive benchmarks comparing all the solvers in Newton with everything in physics, but we know that we really want to surpass physics in terms of speed and throughput. So we're going to put effort there, and I think if community also can come and help, that would be great.
Awesome. And then there was a quick question about are there courses offered to learn more about this topic? So we did share a link in the chat. That's the Deep Learning Institute, NVIDIA DLI. So over there, if you just search for the word Newton or honestly any topic that you may be interested in, you'll get a whole collection of courses, free courses, as well as some talks that we've done at previous conferences and GTCs. So I think that link is your go-to. That would be a great place to see more of these courses. There you go. And that's the link.
Yeah.
Yeah.
Do we have a quick question? I don't think we have a Newton-specific DLI course yet. But
I think we don't probably, but we'll be that's the place to check whenever we have in the future.
Yes, but we will certainly work on bringing for Warp. We have an open source training material that's not part of the DLI, but it's called the Accelerated Computing Hub. Let me find that for you. And then we have other than the training material or examples that are provided in Warp repository that's shipped with the product. We have a separate place called Accelerated Computing Hub. This is run by our CUDA education team. And there we have, if you dig deeper, you can find Warp tutorial for different physics problem. I'm going to share it here, and then you can share it with.
Okay, I got it. I'm posting right now.
Perfect. And hopefully, like in the future for Warp, we are going to probably generate a DLI course as well for this, and as well as for Newton.
Fantastic. And we did see a couple of general questions about learning with robotics. There is a learning path for robotics that I highly recommend. So learning path, just do a search for learning path for robotics. I put it in the chat earlier. That's more general. Isaac touched on Isaac Sim and Isaac Lab. But for those of you who are just getting started, that's a great place to start.
Quick question about when will the Newton cloth simulation be ready for Isaac Lab? I think with the experimental version, it already is.
Yeah, I think we haven't tried training with that, but you can certainly try. It is available. It's in Newton, and you should be able to work with it. I think what we connect Isaac Lab to Newton is what we call selection API that gives you access to articulations or rigid bodies. And I think right now the selection API supports, I think different types of information that you can get passed to lab. So I think from an integration perspective, there's nothing limiting to try this out. But I think the performance wouldn't be there for scaling the same way that you do like normal rigid body dynamics or something we kind of have better performance for. But definitely try it out. I want to call out that the team so it's open source. We are trying to do this, develop this out in the open in GitHub. So we have GitHub issues to basically plan the work that goes there, and that's the same for Warp. We take a lot of input from the community, whether it's a question, whether it's a concerns, a feature request. I really encourage you to send us your, try this Newton cloth simulation in lab, you hit roadblocks, let us know. We would prioritize this and kind of triage this and bring it as we kind of move along. Newton is an evolution. It's going to be an evolution of a product. So it's really a product. So at some point it's going to get there.
Awesome. Okay. We have one more question about, is there an API for your own Python scripts? Could you use PyTorch or TensorFlow, or are you forced to use built-in RL models?
So I think
lab, you could use Torch.
Yeah, I think so. I don't really know an expert, but I think, part of the lab is with Torch. So this should,
I think you can, yes. There is one question, more of a clarification I wanted to make. So the question is how to choose between Isaac Sim and Newton. So the clarification here is that it's not like a clear choice that way. It's more like Isaac Sim is this simulation environment in which you can do a bunch of things like importing robots, setting up scenes, and more. And Newton is like the physics engine that you would use to give physically accurate attributes to all of these objects and to all these things that you put in Isaac Sim. So that's the difference. It's not exactly like either or. It's more like Isaac Sim, and then you have Newton as the engine underneath. Mo, if you want to add anything to that.
Yeah, I think you could still use Newton standalone. That's with a quick viewer, with a solid API and some rendering, basic rendering capabilities is kind of standalone. So you can bring through OpenUSD or other ways your assets, model, simulate, and then visualize or save in a USD your results. And in that sense, you're kind of, and then you can integrate Newton in your own learning environments. Let's say you have something akin to like Isaac Lab yourself, right? The training environment. You should be able to use Newton in that context, and it's standalone, it's open, you can go and integrate it. But if you want to leverage the additional features of Isaac Sim with synthetic data generation, software in the loop, ROS, all those, everything that goes in Isaac Sim, then you can also, once Newton is integrated in Isaac Sim, then you could leverage the capabilities of Newton. Let's say different solvers in Newton, multiphysics, all those things you can leverage an Isaac sim levels. If you can look at it in a kind of a stack diagram where Newton is at their lower base, but is a standalone as well.
Awesome. I think we can maybe go back, spend a few minutes on the ecosystem adoption that you wanted to share, and then we have some more questions.
Very briefly, just wanted to, what I'm really happy and excited about is that we've already seen integrations from some of our key users of Warp and Warp Sim, as well as some new users like from Newton, from the ecosystem. So what you're seeing here is the ETH Zurich RSL lab has integrated, they start using the NPM and the rigid body kind of coupling for heavy equipment simulation. This is a demonstration that shows their work. Actually, a highlight where Camino Solver actually is going to be helpful is modeling a system like the excavator and the or a backhoe or whatnot on the right side, because there's a lot of kinematic loops there. It's not a normal kind of it's not like your humanoid robot that has a flat hierarchy of joints. And Camino Solver, to be released soon, developed by Disney, is going to solve the right side problem. The left side is already solved with NPM. Right now, I think they're using XPBD to kind of, with some limitations, to simulate the rigid body. But the better ways of doing that is coming. Then we're collaborating with Lightwheel. They are helping us build the right asset pipeline and help with solver optimization. They've actually demonstrate how the NPM solver can be coupled with the quadruped for different types of material on the ground. So what we've shown previously and everything you see is only single material. So they extended this to multiple material, and we're working very closely with Lightwheel in that front. Of course, this is not yet real time, but it's very close to real time. And with more optimization and innovation, we think we can get it there and make it even faster than real time. Peking University, PKU, they developed a IPC based solver for fine manipulation and tactile sensing, and they've demonstrated a great sim-to-real transfer for some robotics manipulation tasks. You see here opening microwave with a robotic arm. Style 3D, I talked about their solver that's already in Newton. They actually built this cool demo of a Unitary H1 with a Jensen jacket, which is very impressive, running in real time. They have also some robotics applications. We're excited to work with them on that. Technical University of Munich, TUM, also using Newton for dexterous manipulation. They have their own training environments. They're using Newton. This is an example of where Newton is used as standalone in a kind of a third-party training environment. And here in this video, they're going to show some of that in the Newton viewer. So right now, it's a train policy that's kind of played back, doing dexterous manipulation. This is their training environment, visualized in the simple Newton viewer. And yeah, so there are, although Newton is pretty new, in the last year we talked about Newton a lot at GTC San Jose. Eric Frey from Google DeepMind talked about it. If you're interested in why MJX, or like MJ Warp was much faster than MJX, Warp was faster than Jackson, a simulation framework, he talks in depth about it. He's engineering lead in Google DeepMind. Yuval Tassa from, again, Google DeepMind and the MuJoCo team, and Miles Macklin had a really neat presentation about a follow-up presentation about MuJoCo Warp and Newton and GTC Paris. And Moritz from Disney Research and I had a talk at SIGGRAPH in Vancouver, August, like a few months ago. And that's where Moritz talked a lot about the Camino solver. So go watch that and learn more about it, more in depth. Of course, it's a big team from across these three organizations with different expertise and skill set that's working on this. People expertise in the rigid body, in the soft body simulation, different numerical method. People with expertise in robotics as well as AI. So really dream team could pull this off. In terms of timeline, we started, let's say in June, had an MVP. Around August, we had an alpha. We started the lab integration. We focused on locomotion tasks. Around September, like a few weeks ago at Coral Humanities, we released beta. We announced that we are now part of Linux Foundation. We also released Neural Solver, and we extended our lab integration with manipulation tasks. Sometime around December, we are hoping to have another beta with more polished API and some additional features and more stability from MuJoCo Warp. And then around March 2026, we are hoping to release Newton 1.0 general availability, as well as Isaac Lab 3.0. And that's where we are hoping to have a Camino solver as well from Disney Research. At Coral also, we published Isaac Lab white paper. This is a really great resource that I really encourage you to look at. It talks about Isaac Lab, different APIs and workflows within Isaac Lab, some of its community adoption. Most of it is based on PhysX. This is a very good place where you can see where Isaac Lab is today. And then there's a section for the future and the next generation of Isaac Lab where we talk about Newton, its architecture, some of its solvers, so kind of a more in-depth write-up of what I went through today. Encourage you to look at that as well. And yeah, so Newton is open source under Apache 2.0. Look at it. Right now, it's actually not yet published as a kind of a package, Python package on PyPy. Everything now lives in GitHub, but we are working to kind of finalize that maybe at beta 2 or general availability. We're going to have a Python package published so you can kind of pull it and then import it in your Python environment. And today it ships with a solid, or at least a getting started guide with a couple of good examples that helps you understand multiphysics, cloning, rigid body, different solvers. So I encourage you to look at maybe, I think that's where my presentation ends.
Unbelievable. That was jam-packed. There are so many comments. We were talking about a lot of the questions here, but I got to say, splintered throughout have been a lot of comments, people blown away by what they're seeing on the screen. So thank you so much for preparing, and thank you for picking so many great, interesting questions along the way. I know we didn't get to all the questions, so that's what we have a great resource, Discord, for. I highly recommend people join our Discord server. We have a fantastic channel there called Warp, actually, among other channels. It would be great for you to not only chat with the other users there, but some of our developers try to spend some time there. And then the other thing I'll mention too is that we have a couple of big things happening over the next week. Not only ROSCON is next week, but GTC DC. I'll be there, so hopefully anyone out there who happens to be going, let me know. I'll cover that in the news segment in a second. Are there any final words Mohammed, you want to leave people with before I let you go?
Yeah, just wanted to say thanks to everyone for joining. And I just shared a link to the Isaac Lab white paper. So check that out. Very cool. And also try it out on your end. Let us know how it runs on your different hardware, whether it's the DGX Spark you're trying it on or whatever. Just excited to see what you're developing.
Yes, thank you, Asa. I think one of the things I want to add is that like Warp, Newton also kind of been developed in GitHub. So other than Discord that Edmar mentioned, make sure to bring your questions. When you create a GitHub issue, you can select whether it's a question out of curiosity, it's an announcement you want to make, you build something with Newton, you want everybody to know, or it's a question, it's a bug, or it's a feature request, you can select that, and then that's a great place for the community also. It's not only there for Newton developers, it's for everybody who's actually using or contributing to Newton. So don't shy away of asking your questions there. We do our best to kind of address them as much as possible.
I'm just quickly showing these great comments we're seeing. Fantastic. Okay. Thank you so much for joining us today, Mohammed and Asari, preparing this great information, the great questions, and helping all the community users. So just to reiterate, official support, go to GitHub, community support, user support, come to the Discord server. We do have some developers that hang on Discord server, but don't lean on Discord for official support. Use GitHub for that. You know why? Because we can track things there much easier, and there are many reasons, but not to dismiss the great community support we see from users helping each other every day on Discord server. Speaking of which, we have a study group happening today, Isaac Sim and Isaac Lab study group happening on the Discord server. If you're watching this live, it's in 15 minutes. If you watch this afterwards, it's every Wednesday at 12:30 p.m. Pacific. We highly encourage you. That's led by some great members of the community, some of them who I see in the chat right now. I'm looking at you, Scott Dempsey. So please feel free to join the community there. And developers often pop in that study group as well. So it's a great resource. Mohammed, Asari, thank you so much. I'm going to cover some news for the rest of the gang. So if you're watching, you want to hang out and listen to some news, don't hang up just yet. But definitely like and subscribe to the channel. If you like this material from Mohammed and Asari and you want to see more of it, hit the like button so we know that. That's super helpful for us. All right, thank you guys. All right, so like I said a minute ago, we have some news. We have some amazing news, actually, because we are literally days away right now from one of the biggest events of the year for us, which is GTC. And this is our first one in DC. And that gentleman on the screen right there will be there himself. Not only will he be there, he will be giving a global keynote. This keynote is going to be viewable by anywhere in the world through streaming platforms like YouTube. You can hit that QR code if you want to go to the GTC website, or it's an easy URL. You could just do a search for NVIDIA GTC DC and add that keynote live stream to your calendar. I guarantee you will not regret it. These keynotes with Jensen are just phenomenal. And I can't wait. I'm going to be watching from a watch party myself at Howard University. I'll be there in GTC DC next week. If you happen to be going, let me know. We have a WhatsApp group specific. You can reach out to me on Discord or on LinkedIn. Go to edmar.net. It'll go right to my LinkedIn page. Shoot me a note if you're going. I'll send you the WhatsApp code. But this news I'm about to talk about applies to everybody, because I just found out some amazing news from the marketing team that we have a very specialized team at NVIDIA who works on getting our content out to the world as quickly as possible. And typically that means at conferences like GTC and SIGGRAPH, we usually see the content from those sessions hit NVIDIA on demand, typically about a week or sometimes 2 weeks later. Apparently no more. They're going to try to get this content out within 24 hours of the session. So that means that if any of these sessions I'm about to go over in a minute interest you and you're not going to GTC, do not worry. Just make a note of that session. Go check out NVIDIA on demand after the session, maybe the next day, and you might see it right there. We're going to post updates on Discord in the community. As you'll see, I have some information on SIGGRAPH sessions that are now live in a slide in a minute. But that's super exciting. So again, the following news applies to everybody. So this is a main slide for GTC DC. We have a very exciting full day of sessions planned around physical AI and robotics. We're calling it the Physical AI and Robotics Day. Isn't that creative? So that QR code will bring you right there. And there are sessions throughout the day concerning this that you can watch live if you're there or catch afterwards. There's also a meetup that's happening that night, which is actually full because we started taking RSVPs a couple weeks ago. It's full, but if you're going, I hope to see you there. We also have industrial AI and manufacturing sessions happening. There's a QR code for that. We also have a page outlining all the computer vision and video analytics sessions. Here's a QR code for that. Don't worry if you miss any of these links. We'll put them in the chat or put them in the video description. This is a great blog. NVIDIA accelerates robotics research and development with new open models and simulation libraries. I'm sure it's going to interest many of the viewers watching this live stream. So check this out. 3 ways to supercharge your robotics development using OpenUSD. Also, a quick note, next week, if you are going, you can get OpenUSD certification at the event for free. So you don't need to pay to take the exam. It's actually a very simple way to go, especially if you've done your homework. Nothing to lose, but even if you haven't done your homework, there's still nothing to lose. You probably won't pass if you haven't studied, but it's good practice. So I highly recommend people go and take advantage of that. But here's 3 ways to supercharge your robotics development. Super valuable content. As I mentioned a minute ago, There's Aaron in the background presenting some OpenUSD content from our CGraph full OpenUSD day. All those sessions are now available on demand using that QR code. So even if you can't make some of these events, you don't have to miss out on the great content. Listen, if you're leveraging the physical AI data set on Hugging Face, we want to talk to you. Why? Because we would love to showcase some of your work and upcoming videos that might be used in different events, like, for example, maybe in Jensen's keynote, which usually kicks off with a nice sizzle reel. So if this data set is helping you remove blockers, if it's helping you do work that just was not possible before, absolutely get in touch with us. We would love to hear from you. Go ahead and click on that link if that applies. And then here are some general resources we've got. That first one is our Ed Events calendar, where you can find about all of our live streams, all of our study groups, our office hours, the keynotes, anything big we want to tell you is happening live. We put them right there on the Ed Events page, make it super easy to not only you can follow that calendar, or you can add specific events to your own calendar in just a couple clicks. That forums link will bring you to the forums where most official support is handled, with the exception of what we just talked about on GitHub. There are a couple areas like Warp and like Isaac Lab, where we prefer you to go to the GitHub section, the issues area specifically, because we have developers and we can track stuff there. Discord server, we talked about that many times. Hopefully you guys are all members already. On the ambassador page, is a great place to go check out community resources and learn about our ambassadors, including in a few days, we'll be adding some new faces to that ambassador page. I'm very excited about the next round of ambassadors we're announcing. Check out that page. It's the existing ones, and come back in a week to check out the new ones. I think some of them will be very familiar to people in the community, because they are members of the community that are sharing their wisdom and knowledge with the world. And we love to celebrate them and give them some great credit for what they're doing. And also, if you're an ambassador, we try to make opportunities available to you, whether it's talking to our customers or clients to help your business, or maybe doing a presentation. So if you think this is something you're interested in, let us know. We have a questionnaire we can send you, and we would love to potentially add you to that list. We're going to actually switch screens. I'm going to show you this screen. So I mentioned earlier, we have GTC coming up next week. For some reason, another big event next week, right at the same dates, October 27th and 29th, probably because this impacts different people in different parts of the world. But this is ROSCON 2025 happening in Singapore. This is going to be amazing. A lot of excitement here at NVIDIA across the board for GTC next week and ROSCON. So if this applies to you, we hope you register and attend. It's going to be an amazing event. Lots of great content, lots of amazing speakers. So we hope that people who can attend ROSCON go. I think it's going to be really fantastic. Also, I wanted to share something really quick that I just learned about a few minutes ago, that we have a live stream coming up. We saw some discussion in the chat about DGX Sparks, super exciting release. Now, we know a lot of people have questions. So the NVIDIA developer community team is putting together a live stream for this Friday at 11 a.m. Pacific, 2 p.m. Eastern. This is a developer Q&A. I hope people can attend. So if you got questions, this is a great place to go. Why it was created, who is it for, and what are some ideal use cases. But we also want to answer your questions live. So thank you for joining us today. I think that's it for all the news. I really want to thank our presenters once again for presenting amazing content here. It's been really a fantastic hour. You guys have been really fantastic with the questions. I hope to see some of you at that study group with some of our community members today on the Discord server. If you have any questions, we'll probably need to create a thread specific to this live stream on Newton on the Discord server in the community developer resources category. You'll see where we put all the live streams. Great place to grab information from live streams that happened in the past. Thank you so much. I hope to see you all soon, the next live stream. And there you go. There's that great link from our amazing producer, Amelia. So I hope to see you all online soon. And maybe some of you I'll see next week at GTC DC. We may try to go live spontaneously if I find a good corner of the convention center to broadcast from, give you an update from there. Otherwise, we're going to be we're going to be publishing updates throughout the week. So follow our NVIDIA Omniverse social channels. That's NVIDIA Omniverse on LinkedIn, and Instagram and X, where we're posting a contest from our great community marketing team. That's Greer and Mara. It's going to be a lot of fun. So we'll try to keep the action live, so people who aren't there can also feel like they're at least getting some nice nuggets from us from the floor. We plan to interview some great partners that are there too. All right, thank you everybody. Until next time, thank you for joining us. Bye bye.